Okay, well, now we're ready for 7.2. So I briefly mentioned this last time that in 7.2, what's really going to change is that instead of looking at areas under a curve, we're going to be looking at volumes. Okay, and that's going to change things a little bit. Um, so let's take a look. So we're going to start now. By the way, there's more than one way of doing this. They're going to introduce the disk method here. Later on, there'll be another method for us to consider. And so what's happening here is that we're going to start by taking a rectangle like we have so many times before. But this time we have to visualize what would happen if I took it and I spun it around the horizontal axis. And you can see they've got the graph right here. It would look like a disk. Okay, instead of just a flat surface, it's a three-dimensional surface now, and you can see that it takes the form of a disk. And at the bottom here, they're reminding us, in case you did not happen to remember this off the top of your head, that the volume of a disk is equal to um, pi r squared w. Now, the r is the radius, because remember, now basically a disk is a circle with three dimensions. So it has a radius, just like a circle. And well, that's not a good drawing, but um, and it also has a width. Yeah, in fact, that's such a terrible drawing. I think I'll just grab theirs. Um, let's come back here and grab their their drawing. And you can see, yes, so this is a lot better. So the radius, just like remember with a circle, the radius is half of the diameter. So here's the diameter, and here's the radius. And then the width, because now, of course, a circle doesn't have a width. It's a two-dimensional object, but here we do have a width because it's a three-dimensional object. We'll call that W. And so the volume, if you can imagine filling this thing up with water, is going to be pi times the radius squared times the width. And that means that we can find this volume with an integral. Okay. If we do it correctly, we can create an integral that will give us the volume of this disk. And in fact, there's a reason why it's called the disk method, because it's letting us find the volume of a disk. Okay, so yeah, so here's some others. Now you can see these are a little bit different. What they're going to do is take a series of disks and use those to create another more elaborate object. So once we can have the ability to create the volume of a single disk, we can stretch it out and do other types of objects as well. And you notice the starting point is here, which reminds us of several other examples we've done. We've got the representative rectangle. We've got an interval from A to B, and we have a curve underneath the curve down to the x-axis. And you can see that this would be equal to whatever f of x is, dx. And it's just that simple. But it has to be revolved around the axis. So that's what makes it a lot more complicated. But this piece by itself, the shaded region, is what we've seen before. It's the area under that curve all the way down to the horizontal axis. And that's very simply the definite integral from a to b of f of x dx. Okay, now you notice too that it's no coincidence that this dx is here. Dx is an instantaneous change in x. So remember, we define the integral as the limit as delta x approaches zero, and in the limit, it approaches dx. Okay, anyway, so how do we work this disk method? Um, so the change in the volume, when we revolve it, looks like this. And so We're going to wind up with this as the volume of our solid, where we have the sum of all the individual disks, each with a radius xi, because they're not all the same. If you notice, each of these x's could be different. And so this is the volume of a solid. And that's the formula that we're going to obtain with integration. Okay, great. So we're going to take the limit. By the way, I do want to point out one thing here. This is kind of an issue for switching back and forth between Macs and PCs. I've used these slides on other computers before, and what'll happen is occasionally, if you switch back and forth between a PC and a Mac, sometimes the symbols get mangled. And I'm seeing a couple of these in Chapter 7. If you're using a PC, you're probably seeing something different, but th I don't know what this is doing here. This is something that got misinterpreted because probably these slides were written on a PC, and right now I'm using a Mac. So just be aware that these little weird symbols may pop up from time to time. So um, the only way I can really get around this is to go to a PC and convert these into PDF, but I didn't notice it until too late. So as of right now, this is what we have. But later on, I'll see what I can do about that. Okay. But anyway, um, I think what they meant is delta x goes to zero. And you can see because they're telling us that n goes to infinity. So if the number of rectangles goes to infinity, then that implies a delta x that's going to zero. So finally, this is what we're after right here. V equals pi. And so you can see that as we shrink up delta x, the sum becomes an integral, okay? And we end up with pi a to b, capital R of x, that's our radius, squared dx. Okay, so I think they have an example waiting for us. By the way, they are also mentioning here that you can actually rotate your shape around the horizontal axis or the vertical axis. You'll probably want to do the one that makes it the most straightforward because sometimes the formula in terms of x is extremely messy. You might be able to simplify it by rotating it around y or vice versa. So that's why it's good that there's an option here. But what they want you to see here is this. On the left, that we're rotating around the horizontal axis, of course, which means that the width of this rectangle is delta x. And so this is the formula that we just showed a minute ago. So if you rotate it around, you're going to wind up with the volume of its disk. But if you try to do it from left to right, you'll have to make some changes. So for one thing, the graph is different. Everything's in terms of y's. As we saw in the last section, remember we did some integration with respect to y as well as x. The interval has to change. You notice how it's c to d now instead of a to b. R is expressed as a function of y instead of x. And so the resulting formulas are going to be a little bit different too. Here, for example, we have the formula we just derived a second ago. Pi times the integral of r of x dx. And then this one will look like this. You can see the only real change is the upper and lower limits of integration and the fact that we changed the variable. All right, so let's sneak that in here. Okay, so let me make sure everything worked out fine. Yeah, here we go. Oh, those got moved down. That's why this happened. All right. So again, we have a different limits of integration, and everything is in terms of y. But it's the same process. Okay. All right. Let's see what examples they have. So here we have uh, now, by the way, if you notice, this one is not really well, it's they call it a solid of revolution, and that and it's going to be hard to visualize this, of course, but if you do rotate it around the horizontal axis, this is what it should look like. And the function is the square root of x, a sine x, and it looks like we're only doing this over the interval from 0 to pi. Okay, so r, in this case, is the height of the curve at the representative rectangle. And that brings us up to the function radical sine x. Okay, so capital R, in this case, because we're reaching down to the axis, r of x is just equal to f of x. It won't always work out that way. Fine. And by the way, since we're rotating from top to bottom, I guess, let's go copy this formula again to remind ourselves what we're attempting to do here. Just for as a point of reference, um, I'm going to copy this down here so we can see it better. Okay, so we need the R of X. And like I said, the interval is 0 to pi. So we can calculate the volume of this solid, which it kind of looks like a football, doesn't it? Yeah. Or, all right. Anyway, so from 0 to pi, and remember the function is radical sine x. Now, it looks like it's going to be a very simple case because um, when you square the square root, of course, you just end up with the original value. You're going to have the integral of sine x dx. Okay, so now we went over this when we were reviewing. Um, I now, by the way, don't forget there are charts in Brightspace that you can use. If you forget, let's go look here, tables. And one of them, uh, I don't think there's a separate one for trig integrals, but this one, let me just check this one. Just in case you forget, here they are. Or you can look at the back of the book. Some of these came from the book. Some of these I wrote out myself. All right, so let's get this up and see if it reminds us the integral of sine x, okay? I'm sure it's in here somewhere. Let's go find it. No, wait. Oh, almost, almost. There it is. So just remember, The integral of sine x. Now, this is u, which is meant to be a function of x, but for just us x, the integral of sine x dx is the negative cosine of x. Okay. Now, since we're doing a definite integral, we don't need the constant. All right. So just, don't forget that these tables are there. They're there to help you out. So you don't have to be constantly looking things up. All right. So now we can evaluate it. Actually, I'm going to move the negative out here. So cosine pi minus cosine x, 0 rather. All right. So now, if you don't happen to have cosine pi memorized, you can go to your calculator, but keep in mind, I have the TI-84. If you're going to take the cosine of pi, make sure you're in radians mode. Okay. So on the TI-84, it has many different modes to choose from. If you go to the mode button, which is in the upper left-hand corner, you'll see them all. It's a long list. And the one, two, three, fourth from the top, it gives you the option of radian or degrees. So you highlight the one you want, hit enter. If it's already there, of course you're fine. But if you're not, if you're in degree mode, you have to arrow over there and hit the enter button. And in this way, it'll understand what you mean by cosine pi. Okay. So then when we come back, there's a cosine button on here. Now to get a pi on this calculator, it's not in a super obvious place. Um, what you have to do is this. You type cosine, second, and then the exponentiation button, which is directly above the division sign. If you see directly above it, you'll see a tiny little pi up there. And you'll know you did it correctly because you'll see it in the window of the calculator. Close the parentheses, hit enter, and you'll see that it's -1. Now, for 0, you just hit cosine 0. You're all set. And that happens to be +1. And so you've got -pi, -2, which is 2 pi. Right. So, um, good opportunity to get some review with that calculator. So the total volume is 2 pi. Okay, now, as if this wasn't enough, look at this case. You've got a disk, but there's a hole in the center. It if you've ever seen I'm not all that familiar with tools myself, but if you've ever had to like build something yourself, when you're screwing things together, you find these little round discs with a hole in the center, and they're called washers. I know next to nothing about them, but that's what this is all about. Those little washers that you use, it helps strengthen up the connection, I guess, when you're screwing something together. And so because the angle, the representative rectangle doesn't reach all the way down to the horizontal axis, if I spin that around, you can see what's going to happen. We're going to wind up with a big hole in the middle. Um, I guess it would have sounded silly if they called it the donut method, but that's kind of what it is. So what this means is that we have to take into account not just the radius of this thing, but there's a second radius here, this little r. And so they're going to give these the names, just to make sure we know which is which. We'll call the capital R the outer radius, and this becomes the inner radius. Okay. So the difference between those is what we're actually rotating around the horizontal axis, and that will determine the size of this hole. So we have to take into account when we solve for the volume of this object that we're creating. And in the slides, they also remind us, um, you probably remember this from your travels, that the plural of radius, well, it's not radiuses, it's radii, believe it or not. Yeah, that's right, radii. So anyway, now we're going to need to change our formula to take into account both the inner and the outer radius. And so this is our new formula. And you can see it's almost the same, except for that new inner radius that wasn't there before, of course. And using this formula is referred to then as the washer method to distinguish it from the disk method. Okay, so compared, let me just go grab this one. Now, of course, just like with the other one, we can rotate around the horizontal or the vertical axis. This is the formula for the rotating around the horizontal axis or up and down. Let's compare these side by side. This is the disk method. And all right, I'll tell you what, just so you can see them all at once, I'll copy this down here. And yeah, you could see there's literally only one difference, and that's right here. Okay, so I guess we've got an example coming up next. Ah, all right, here we go. And you can see why this one requires the washer method because what we're seeing here does not reach all the way down to the horizontal axis. What's tricky is trying to visualize what these things look like when they're rotated like that. I mean, it's a good thing this is here. I would have had no way of knowing. So, um, anyway, so how do we find this region? Well, first of all, the function capital R equals radical x because that's the actual f of x here. And then the lower, this one down here, I guess you could think of that as g of x. Um, that's our x squared. That's the bottom one. So again, you see how this compares with calculating the area under between two curves, rather. The difference here is that it becomes a solid when we rotate it. So we also need to know that the interval over which we're doing this is 0 up to 1. All right. So let's grab the formula and let's do it. So A is 0, B is 1, capital R of x is radical x, lowercase r of x, the inner radius is x squared. All right, so we should be good now. So then we substitute. So capital R of X is radical X, but then we square that. And then lowercase r, the inner radius is X squared, which again is squared. We subtract one from the other. And of course we have dx. And now it's just a straight ahead integral. So let's just fill in the details. So when you square radical x, of course, it just becomes x. And when you square x squared, it becomes x to the fourth. All right, so now let's apply the rules of integration that we know so well. So of course, we're applying the power rule in both of these cases. All right, great. So the first thing we want to do is factor out those constants, those pesky constants. And then we make the substitutions. All right, let's see what we've got. So we've got pi times 1/2 minus 1/5. And of course, now we need a common denominator, which let's use 10. So we ultimately end up with 3 pi over 10. Okay. And that's our volume. All right. Now sometimes we have a much more complicated situation here. It's actually possible to do this in two stages because if you notice, like in this diagram, there's a portion of this where we reach the horizontal axis and sorry, in this case, the vertical axis, and a portion where we don't. It's almost like two separate problems. And so what we would have to do in a case like this is treat them separately, integrate both this piece and this piece and add up the results because you can see the properties are very different from each other. So, and of course, on top of everything else, we're rotating it from left to right. So this one is a bit of a mess, but you can see that from zero to when y is 0 to 1, it's a very simple shape. In fact, it's a rectangle. And then directly above it, though, we have a curve. And that one, we would need to use the same techniques, except from left to right. Okay. So so what they're telling us is that the outer radius in both cases is 1. Okay, now remember the outer radius is being defined with respect to the vertical axis. So if you go from left to right, you can see that it is 1. So for both cases, capital R is 1. That makes things a little easier. Okay, let's make a note of that here somewhere. What separates the two is the lowercase r. Now, down here, there actually is no lowercase r. It's just 0. But here, actually, oh, I just realized, oh, my mistake. No, these are y's. Sorry. So used to writing x's. Don't forget, these are y's now. So here y is just, it's because we're reaching the vertical axis, but here it would just be the function itself, which is radical y minus 1. Okay. So, and then down here, the range of values for y is 0 to 1, and down here, up here on the top, it's 1 to 2. So what do we end up with? Okay, so you're applying the same formula twice. Okay, so let's go write that down. So when we're doing x's, we use this formula, but we're going to change that to y. Okay, so let's do that. All right, actually, I'll tell you, let me just go up here and copy this real fast. Yeah, so because all we really have to do here is change those x's to y's, and the difference here is that we're going to use it twice. All right, so we're doing this in two stages, of course, as you can see. So we'll start with the bottom one first because it's really simple. We have from 0 to 1, the outer radius is 1. The inner radius is 0. Wow, that couldn't be any simpler. And then the one directly above it is, so we'll have, again, the outer radius is 1, but the inner radius is radical y minus 1. And of course, don't forget to square that. All right. Now, the first expression will be very simple because you can see it's going to be a constant. So let's deal with these one at a time. Um, we'll start with the first one. Um, 1 squared minus 0 squared dy. Okay. So of course these constants reduce to 1, then we have dy. When we integrate dy, it becomes y. And when we evaluate it, it becomes 1 minus 0. So the first part is just pi. Great. Now the second one, the challenging one, let's try that. Oh, I just realized, no, there's a problem here. This isn't 0 to 2, it's 1 to 2. If you go back to the graph, you'll see, yeah, it's from 1 to 0 to 1. This part is 1 to 2, so we have to fix that. So this one is going to be 1 to 2. All right, now we're good. Let me just make it a little neater, sorry. Everything from 1 to 2. So of 1 squared. Of course, when you square radical y minus 1, you'll just end up with y minus 1. And the 1, we'll just leave it as 1. All right, and what does that give us? Okay, and now I can simplify it a little. So we have 2 minus y dy. All right, so when we integrate 2, um, let's see, let's break it up into 2 pieces first. That way it'll be easier to see what we're doing. Yeah, this is better. Okay, great. Now this 2 can be factored out. I always want to factor them out. It just makes things so much simpler. All right, now what does that leave us with? So we got 2. Now when you integrate dy, it just becomes y. And of course, the integral of y is y squared over 2. All right, so let's keep evaluating it. This one is 2 squared over 2 minus 1 squared over 2. All right. 2 times 2, 1 rather. And here we've got 4 halves, which is 2, minus 1 half. So we have pi times 2 minus 2 plus 1 half. So we end up here with pi over 2. Now remember, this is just the piece on top. We found that this area is pi over 2. And the piece on the bottom, which we evaluated first about a minute ago, we found it pi. Okay, it turned out to be pi. Great. So now we just add them up. The total area would therefore be pi plus pi over 2. And that's, of course, just 3 halves pi. So they kind of threw a bunch of curveballs at us. First of all, they gave us an area that is like essentially broken up into 2 pieces, and then on top of that, they made us rotate it from left to right. But we managed. Okay, it's just a little bit messier. 3 pi over 2. Very good. Um, Now here they're doing something a little bit different. Now, all of a sudden, these are what are called solids. Um, they can have almost any shape you could imagine. And the idea here is that what you're actually doing is taking slices of the solids and adding them up. Okay, now if you notice here with this thing, and I don't think there's even a name for this, we've got the representative rectangle here with the width of delta x and if you notice, they've laid it out a little differently. The X and the Y axes, the reason why they're laying down here is because when we have a three-dimensional figure like this, it's standard practice to have a third axis called Z. Okay, and that's what they're doing here. Then this one can be X. It doesn't really matter. One of these is X, one of these is Y. So if you're trying to show a volume like this, you really need these three-dimensional axes to show it properly. So the height is the z-axis, and so um, the width is being calculated with respect to the x-axis. There's going to be a height involved here too. And so we're slicing across this thing and adding up the slices. Yeah, so it's a little bit different than what we're used to seeing. So the volume that we end up with is here, but that A is the area of each slice. Okay, so in other words, for each slice, the area is A of X, the volume is the sum of those areas. All right, and then if we do it with respect, now if you notice, here the representative rectangle is on the x-axis. We could also do this on the y-axis. Okay, if we're assuming this is the y-axis. And you can see the only difference is the upper and lower limits of integration, and now it's A of y instead of A of x. We can do either one. Usually we just pick the one that's got the least messy functions for us to deal with. Oh, look at this one. Um, it's kind of like a pyramid, I suppose. Um, and so they're running, here we are. So what they're doing is this is meant to be the slice. And you can see this we know how to do. We're taking the area between two functions. And here's our representative rectangle. And this is being done with respect to the horizontal axis. So everything is written in terms of x. And so that what they're going to have us do is first find the area of the cross. Okay, so here's our representative rectangle. Now the area itself, though, if you notice that blue shaded region is actually a triangle. And the area of a triangle, as you recall, just any generic triangle is 1/2 base times height, which in this case is this would be considered the base, and this would be the height. But they're throwing a clue at us down here. If you notice, these two sides are equal to each other, and this becomes known as an equilateral triangle. And it has its own unique formula for the area. So instead of using 1/2 base times height, instead we're going to look at radical 3/4 s squared. S is the side that's the same for both. In other words, this would be S. Whatever that is, the distance from the axis to 2 is the side. So we're going to use this formula instead of this one to come up with our results. Okay, so with that being said, the base is the vertical distance between those two functions, f of x minus g of x, which means here's our f of x, 1 minus x over 2. Here's our g of x minus 1 plus x over 2. Oops, sorry, that's g of x. And then algebraically, that becomes 2 minus x. And then radical 3 over 4. Now the base, we're using base. We could have used s squared. It's the same thing. Is going to be radical 3 over 4 times 2 minus x squared. So they're going to have us integrate that formula between A and B, which in this case is -1 and +1. Okay. So, oh, sorry, it's not -1 and +1. We're looking at this direction. Okay, that's better. All right. So they go ahead and do that for us. And you can see, well, they've done all the work for us. But if you were to integrate this, you'd end up with 2 radical 3 over 3. And that becomes the volume of this very complicated looking solid because of the fact that the cross section, as it's called, or the slice, has area equal to radical 3 over 4, 2 minus x squared. Okay, now the way they gave it to us is a little bit convoluted here, but given an area for a cross section, and so you imagine the cross section means a slice. So you're effectively adding up all the slices to come up with the volume. And so that's why we're able to use integration to come up with this volume. Okay. Now, for each case that they may throw our way, they have to explain to us what to do about the cross section. They have to tell us what it is because these shapes can be very, very bizarre, as you can see. They can't just leave you guessing. In some cases, it's just a simple rectangle, but they have to tell us what it is. But once you've got that, it's actually a very straightforward process because you're just taking the volume is nothing but the integral, the definite integral from a to b of a of x dx. Okay. Now in 7.3, this is 7.2, by the way, 7.3, which is just coming up next, we have one more technique for finding volumes, and it's called the shell method. Okay. Um, the shell method, now look at this thing. Let's say that it's a little bit more complicated. We're creating cylindrical shells. Okay, so it looks like a pipe, basically. And so the logic is very similar. We're just going to rotate this around the axis. We're going to integrate the area here. And then, but it's meant specifically for this kind of case. Okay. And I think that's the last one. I don't think there's any more. We're going to be doing something a little bit different in 2.4, sorry, 7.4. But so these would be the shapes that we need to know how to use. And then in 7.4, we're looking at, I believe, area or distances along a curve. And then in chapter 8, by the way, we're going to get to see some much more complicated integration techniques. Now, we know a lot of the important ones, but there's a lot more to come. So chapter 8 is very long and very intensive. And when we're done, we're going to be experts in integration. Okay. There's a lot more out there that we didn't use or see in Calc 1. So that's going to take a while. So we'll wrap this one up quickly and we'll get into 8 and we'll spend quite a long time learning all these very powerful techniques for integrating different kinds of functions. And honestly, on integration is a much more complex process than differentiation. So it's going to take a while to get through them all. And even then, we're not going to learn every single one of them, just some of the really powerful ones that we haven't seen before. So that's where we're heading with this. Okay. So anyway, in the meantime, we'll stop right here. Next time we'll wrap up the shell method and 7.4, and then we can start our study of more advanced integration techniques. I think you'll find it very interesting. All right, so I'll see you then.